Hello, everyone. My name is Eric Javier. I'm an electrical engineer. I'm joined up here by John Cars, which is also an electrical engineer, and Nick Raftakis, which is our computer engineering counterpart. First and foremost, we would like to thank our technical directors, Jeffrey August, Luca Petrovic, and Eric Forte, as well as Mike Smith, which has been consulting on our project every now and again. So thank you very much. So our project, we've been working with Schneider Electric. Our project is to redesign Schneider Electric's SMX 1000 uninterruptible power supply. The motivation came from a new Department of Energy power consumption standards for a plethora of different items on the US market. One of these items being uninterruptible power supplies. Schneider Electric's SMX 1000 currently stands at 98.3% efficiency, and the new DOE mandate is that all UPS devices be at 98.5% efficiency. So this means that our best anticipated outcome was a complete redesign of the system in order to be adherent to the new standards, and John's going to take you a little more through how we went about that process.
Hello? Okay, so as Eric said before, we were tasked with redesigning several sub-circuits in order to increase the efficiency of our UPS. Unfortunately, we can't show any schematics due to proprietary information, but we've included some simplified schematics to the top right. The first of these is IC412, which is an error amplifier circuit. Basically, this circuit established our methodology for decreasing power consumption for the rest of the year. First, we obtained a simplified schematic, then we put it into PSpice for simulation. Then we used the transfer function to graph the magnitude and then the phase over the frequency. After that, we hand-derived our own mathematical transfer function, for which we optimized by increasing the resistance and decreasing the capacitance in order to retain the shape of the original transfer function. In this graph specifically, the original circuit is in blue, and then our circuit is in red. You can probably see they're not exactly the same, but that's because we didn't use standard components. And that's just one thing we learned, is that you can't hand tailor every circuit. You need to use standard value. It's just a lot more practical. The second of these is also another amplifier, but it's a bit more complex, as you can see in the simplified schematic. Methodology is basically the same: obtain the transfer function, optimize it, and then graph them over each other. You can see up here that there's only appears to be one line. That's because we actually nailed it, and they line up perfectly over each other, except this circuit is 3 times more efficient than the original. We kind of pivoted this semester and worked on an optocoupler disconnect switch. The gist of this circuit is that there is a signal on the right from a simulated signal from a microprocessor, which turns on an optocoupler and shorts a charging circuit to turn the battery off when it's completed its charging cycle. The reason why we used an optocoupler is because the two sides of the circuit weren't previously connected and were located at different potentials. So if there's any physical contact, there could be damage to the system. An optocoupler uses an LED to induce a current in a transistor on the other side, so there's no physical contact, therefore no damage to the system. The optocoupler disconnect switch is a driven N-type FET, and it has current leakage protection, over voltage protection. It can take an input of up to 400 volts, and it's active low. Next, Eric will talk about our best anticipated outcome.
All right, so as I mentioned before, our best anticipated outcome was a increase in 0.2% efficiency. Now, Jack talked to you a little bit about the specifics of how we went about this. I'm going to go more top level. First, this meant that we had to identify sufficient inefficient sub-circuits within the system. We then had to analyze these circuits to see how they worked, not only internally, but how they also interacted with the rest of the system. Once we understood how that worked, we had to propose changes to this to the circuit, keeping in mind circuit functionality as well as how to reduce power consumption. And then we had to implement and test those changes to see if the circuit retained its functionality, as well as if power consumption was indeed reduced. So the big question is, did we achieve our goal? Unfortunately, we did not. Our best anticipated outcome was a full redesign of the circuit, of the system. However, we did redesign several different sub-circuits, as you just saw. The biggest one being the optocoupler-driven N-type MOSFET, which with correct implementation and a new bias DC supply can save a considerable more amount of power than what is currently being implemented. The team also feels very confident that we left the project at a very good point, and it shouldn't take much more work to completely finish the design, get the printed circuit boards, and do the DOE testing. Now Nick is going to talk to us a little more about the software side.
So some of the things I worked on this semester strayed away from some of the work that Jack and Eric accomplished. I worked with a firmware engineer at Schneider Electric's Kingston location. Our goal was to use Smart Connect to create a QR code generator to test different error messages for the UPS devices. Now, Smart Connect is a product offered by Schneider Electric that allows cloud connectivity with uninterruptible power supplies. This allows monitoring and control for one or more UPS devices via a customer's web browser. This special project was a proof of concept of how QR codes and the user interface of the device can enhance the customer's experience. These codes represent different device statuses and can be easier to access rather than using a web browser. So the project consists of 2 parts, a Java-based QR code generator functioning as a UPS, and a simple Node.js website that parses the URL encoded by the QR code. In the first example, we have a QR code as shown to the left that contains the device information. After scanning the QR code with the smartphone, we are brought to the corresponding web page as shown to the right. Now this web page displays information such as the device serial number, the MAC address, the error number, and the corresponding error description. In the second example, we create a new QR code for the same device. After scanning it with the smartphone once again, we're brought to its corresponding web page, this time with a new error number and new error description. Now throughout the semester, we created different error numbers, descriptions, and device serial numbers in order to get a variety of different test results. We would like to thank our technical directors, Jeffrey August, Luca Petrovic, Eric Forte, and Mike Smith for all the hard work they did throughout the year to help us achieve our goals. I'd also like to thank Dr. Sunak for putting together the Capstone program. Thank you.
Thank you very much.